Hi there. I'm going to cover some circular motion fundamentals for students that are taking Physics C. Let's get started. So I have copied over the relevant equations from your equation sheet here. As for this V is equal to WR, this only holds true if there is no slippage. When you slip, the object is translating and is considered part of linear motion. It's not likely to encounter a problem that includes slippage, but if that's the case, just remember that velocity will no longer equal to WR, but will be greater than. I also want to make a comparison between these angular motion quantities shown in black here and the linear motion quantities shown in green right below them. As you can see, the only difference between these relationships is the substitute of linear quantities with angular. So velocity becomes angular velocity, acceleration becomes angular acceleration, and position becomes angular position. Because we know the differential and integral relationships between linear motion quantities, we can extend these to its angular quantities. So to go from angular position to angular velocity, you take the derivative of the position with respect to time. To go from angular velocity to angular acceleration, you take the derivative of that angular velocity with respect to time. And to go from acceleration to velocity, you take the integral with respect to time. And lastly, to go from angular velocity to angular position, we need to take the integral velocity with respect to time. And I'm going to put this off to the side here. This is a good mental note. So again, these all hold true if there is no slippage. Another important definition is revolution. So this equation defines a revolution in its angular quantity as completing a 360-degree turn. And this equation defines revolution as its linear quantity as the entire distance around the circle, or essentially its circumference. An example problem, and most common type of problem that you will see, is kind of like the following. If your angular acceleration is equal to 20 radians per second squared, how many rotations would a hoop complete if its R is equal to 2m, and this is going to be between 0 and 2 seconds for its time. All right, well, so we want to know how many rotations, so how many revolutions would this hoop complete? Well, all we have is acceleration. Well, that's fine because we can get to position by taking the double integral of acceleration. So the integral of acceleration is going to equal to angular velocity. So the integral of 20 is going to equal to 20t. And for position, you take the integral of velocity. All right, so we have the equation for angular position. Now we want to do it between 0 and 2 seconds. So that means that 10 times 2 squared minus 10 times 0, well, this is going to give us 40 radians. Again, if you're having difficulties with taking integrals or derivatives and understanding what limits are, I refer you back to my first video on math fundamentals. All right, so we traveled 40 radians. So what does that tell us? Well, again, we want to know how many revolutions, which is either represented in angular position or in distance. Because we have radians, let's go ahead and just stick to this equation here. So we have 40 radians, and we have 2 pi, which the units is in radians, and 1 revolution. So these units cancel out, and you divide 40 by 2 pi, you'll get 6.36 revolutions. Now, if they did ask how many complete revolutions occurred, you would say 6 revolutions, because it did not complete the 7th one entirely. The next very common question to follow up is, how far did the hoop travel across the ground? All right, so very simply, we know that we had 6.36 revolutions. And the fact that the circumference is 2 pi r, so 2 pi, and then the radius is equal to 2. So 6.36 times 4 pi is going to give us about 79.92 meters. Now, there are usually 4 types of problems that you'll see on the multiple choice or the free response portions. However, it's not very common to get bank curve problems on the free response. I believe it's happened once in the past. It's a great way to conceptualize the summation of all your forces and deriving your centripetal force. So still a very important fundamental, and it's most likely that you'll have at least one question on the multiple choice about these types of problems. One thing I want to make very clear before we start these FBDs is to never draw centripetal force on your FBD. Centripetal force is a summation of all your forces or your unbalanced forces. Usually those unbalanced forces are from the tension in your string, the normal force from your surface, or the friction force from your surface. Therefore, your unbalanced forces then create an acceleration because F is equal to ma. The only thing that makes centripetal acceleration special is that because we are moving in a circular motion, that centripetal acceleration can be re-represented as a constant velocity squared over some radius. All right, so let's start with the first problem. This is really, really common to have, which is a mass on some sort of string around some sort of pivot point here, with some radius r for that string. Again, the first thing you always want to do is draw your FBD. So we have the force of tension from the string coming this way, and we also have the force of gravity going down. And let's say that the ball is moving at this velocity, which is going to be tangent to this string. And if you remember from my previous videos, if you ever see a diagonal, the first thing you should think of is, I probably should split that up. So this is going to be your force of tension in the x direction here, and it's going to be the force of tension in your y direction here. This is given some sort of, let's say, theta. So let's derive your force of tension in the y direction then. This is going to be equal to your Ft, because this is adjacent, cosine theta. As for your force of tension in the x direction, Ft, because it's opposite, sine theta. Now let's look at centripetal force, because we know that this has some sort of constant velocity. Centripetal force is equal to the summation of all your forces. And if you can tell by this diagram, the only unbalanced force that we have is this force that's acting in the x direction. And we can see that the force of tension in the y direction is going to equal to the force of gravity. So that means that we only care about the x component. Therefore, we can rewrite this. So our centripetal force, mv squared over r, big R, is equal to ft sine theta. Therefore, usually you'll be asked to define the force of tension in the string. We can rewrite the force of tension in the string as mv squared over sine theta. Now let's look when the ball is straight up and down and not at an angle as shown here. Still again with the same velocity v. Again, let's draw our free body diagram. So we have force of gravity and now force of tension. Again, we said that your centripetal force is equal to the summation of all your forces. Well, we only have forces acting in the y direction. So we have f of t minus fg. All right, and let's plug in fc, which is mv squared over r, is equal to ft minus mg. And we can redefine ft as equal to mv squared over r plus mg. So let's look at the last scenario where we have the mass or the ball positioned above its pivot point. Again, let's draw our FBD. So we have force of gravity always pointed down. We also have this force of tension as well pointed down because force of tension is always going up the cable. So let's do our centripetal force equation. Now, even though those forces are pointed down, I'm going to sum these forces. And the reason why is because when we're doing centripetal force equations, anything that's pointed towards the pivot point should be considered positive. Anything pointed away from the pivot point should be considered negative. Again, if this is too confusing for you, if you want to keep your directions, any forces pointing downwards is negative, that's completely fine. But you need to be very, very careful for the sign for centripetal force. If it's going towards the centripetal force, they need to be of the same sign. All right, so Ft plus Fg, Ft is equal to centripetal force minus Fg, which is equal to mv squared over r minus mg. Now what you should notice, very simply, is that this equation is greater than this equation by a factor of 2 mg. This is the maximum tension that you will experience on a string, is when it's at its lowest point, where the pivot is above the mass. And this is the minimum force of tension that you'll experience on the string, which is when the ball is above the pivot point. Now, I'm sure you've experienced this effect before. When you are rotating the ball at the end of a string in a circular motion, you'll feel the pull of the string to be the greatest when the ball is at its lowest point, and to be the least when the ball is at its highest point. So this is the minimum amount of force of tension that you'll experience in this string. This is the maximum force of tension that you'll experience in the string. Oh, and I forgot an R here. This is the force of tension that you'll experience in the string when the ball is at some sort of angle. All right, now let's look at an example where we have some sort of object, let's say a car, that is rotating about a circle that's on a flat surface and has friction. Now, because the car is not levitating, so that means it's not accelerating in the y direction. So if we draw the car from this view, we have the force of normal from the surface and the force of gravity pointing straight down. Now, because again, we aren't accelerating in the y direction, these forces are equivalent to one another. And therefore, the only force that's acting upon this car has to be the force of friction. That is the unbalanced force. And it's directed towards the center. Therefore, we can write Fn is equal to Fg, which is equal to mg. And the sum of all of our forces is equal to force of friction, which is equal to mu mg, which will then equal to our centripetal acceleration, which is equal to mv squared over r. Let's say that this radius is r here. So let's simplify this equation. So both masses cancel out. This is very, very common. And the velocity that the car will need to go at to keep from slipping will be equal to mu g r, or the square root of the coefficient gravity times r. All right, let's look at a car which is on a bank curve and is frictionless. As you can see, my car is slightly levitating. However, let's just assume that the wheels are touching the ground, as so. So first thing, always draw your FBD. Your normal force is going to be perpendicular to your surface, and your force of gravity is going to be directed downwards. Now this is very different from our kinematics and other FBD problems. Even though we do have this sort of ramp option, we have centripetal force in play here. So there are rules when it comes to this. First, do not rotate your axis. Fn, your normal force, does not equal to all downward forces. Again, because a portion of that normal force is going to be contributing to the centripetal force. And like I said before, towards center of your circle that you're going about, so it'd be, this would be your center, is going to be positive. So the first thing you do, as always, is split your diagonals. So we have our normal force. And the reason why I drew it in this manner is because the theta that I have here is going to equal to the theta that I have from this ramp or this bank. Where you define your theta, again, is very important. If you try and define your theta here,
this will no longer be the theta that you see on your bank. It is going to be 90 minus the theta that you see on your bank. So you want to be very careful for where you define theta because it can change your answer significantly.
So we have the x portion, this normal force, which is Fn sine theta. And this is Fny, which is cosine theta. Now, since the block is not levitating, or I guess in more technical terms, not accelerating in the y direction, sum of all the forces in the y direction have to equal to 0. So that means that f of n in the y direction, this component, minus f of g, because it's pointed downwards, is equal to fn cosine theta minus fg, which is equal to 0. So your normal force is going to be equal to your gravitational force over cosine theta. Again, this is very different from what you've seen in previous problems, where your normal force is usually less than your force of gravity in previous kinematics problem, but now your normal force is going to be greater than your force of gravity, because cosine of theta, the greatest value you can have is 1, and that's very unlikely that you will have that scenario. So force of gravity over a fractional number, then force of gravity. All right, so then you're going to solve for your centripetal force. So your F of C is equal to sum of all the forces. And as you can see, some of the forces in the y direction is equal to 0. So that means that the only force that is unbalanced is your x component. So we have your normal force, sine theta. And then we solved for normal force in this previous problem, so we can just substitute that in. Oh, well, this is interesting. Fg, let's rewrite it like such, sine theta over cosine theta is the same thing as saying tangent theta. So this is equal to force of gravity, which is equal to mg, and this is equal to tangent theta. And then lastly, you might be asked to solve for the velocity to keep the car from sliding up or down the incline. So your centripetal force is equal to mv squared over r, which will now equal to mg tangent theta. So our m's will cancel out, and we'll get v is equal to square root rg tangent theta. So this is your ideal velocity. So when your velocity is greater than the ideal velocity, your car is going to want to slide up the incline. And when you have a velocity that is less than your ideal, then you're going to want to start sliding towards the center. And you can kind of experience this with your car. That's why when you are driving and you go around a curved road, you want to deaccelerate. Because if you go at too fast of a velocity, you're going to start to feel as if your car is pulling you
away from the center of the curve.
Now let's look at the last scenario where you have a banked curve and it's going to be with friction. First thing, draw your FBD. Force of gravity, your normal force. There's two ways that your force of friction can be directed. Your force of friction can be directed towards the center, or it can be directed away from the center. And it depends on, again, these scenarios. Your car, if you go at too fast of a velocity, is going to want to pull in this direction. But because of friction, because friction opposes velocity or is in the opposite direction of velocity, it's going to be directed downwards. And if your velocity is less than the ideal velocity, so that means your car is going to want to have a velocity going inwards, your force of friction is going to be the opposite, which is going to be pointed outwards. So you need to draw your force of friction based on what this velocity ideal value is. So I'd always solve for this first if given this problem, if they're asking for some sort of calculation, so you can understand which direction this is going.
However, for most cases, force of friction will be directed towards the center of the bank.
So the first thing you always want to do is split your diagonals. Again, we're going to consider that the force of friction is going towards the center. So let's do this. We have our force of friction. And again, how we define our theta is very important. For this scenario, our theta, for it to equal that of the bank curve, needs to be defined here and here. So your force of friction in the y direction is equal to force of friction sine theta, force of friction the x direction, cosine theta. Then we have our normal force. The x direction is equal to Fn sine theta, and its y component is equal to Fn cosine theta. Again, since the car is not levitating, your summation in the y direction is equal to 0. So this is going to be equal to your normal force in the y direction minus your force of friction in the y direction minus your force of gravity, which is equal to Fn cosine of theta minus mu Fn minus mg, which is equal to 0. And in this case, we have Fn cosine of theta minus mu minus mg is equal to 0. So we can solve for our normal force as mg over cosine theta minus mu. And if you want to solve for centripetal acceleration, that's going to be the sum of all your forces, unbalanced forces. So as you can see, that's not going to be in the y direction. That's only going to be purely in the x. So that's going to be equal to your force of friction in the x direction plus your normal force in the x direction. Again, these are pointed towards the center of the circle. So these are going to be positive even though they are pointed left. So that's equal to force of friction cosine theta plus your normal force sine theta. So this is going to equal to mu f of n cosine theta plus Fn sine theta. We can factor out the Fn, which is equal to mu cosine theta plus sine theta. And then you can substitute your Fn here. So this is going to equal your centripetal force. And if you want to solve for your velocity, you can rewrite it as v equals square root of Fc r over m and plug in Fc for this equation. And let's say your force of friction was in the opposite direction. So your y component, x component. So you can see that the x component is directed to the right, which is away from the center. But your normal force, however, is pointing to the left. So when you have the force of friction pointed away, you're going to have a negative placed in front of these equations because, again, we are directed away from the center. Now, one last thing before we move on to rotation in the next video. Angular acceleration does not equal to centripetal acceleration. So your torque is not equal to your centripetal force. And this may be intuitive for some people and may not be for others. One thing I want to define is your location of your pivot. So for centripetal acceleration or centripetal force, your pivot is not located on your mass. For angular acceleration, your pivot is located on your mass. And when I say that, let's look at examples here where we have the string. This point right here is considered your pivot. It's not located on the mass that you're analyzing. As for this car, the location of the pivot is the center of the circle, and it's not on the object that's rotating about the circle. And same thing with these cars, these banked cars. The location of the pivot is at the center of the circle. So when we're looking at rotation, we're going to see that the pivot's going to be located on the mass, and we're going to start analyzing those scenarios. All right, that's all I have. Thank you so much for watching my video. If you have any questions or concerns, please let me know. If there was anything I didn't cover, please comment below. All right, thank you.